Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We are discussing Wilson's renormalization group. Let's begin with a very brief recap. So Wilson starts off with a d-dimensional continuum formulation of the ON symmetric Ginzburg-Landau theory. We are working with the vector version of that theory where the fields are ON vectors. The theory has a momentum cutoff which we have discussed at length. And the coupling constants of this theory are going to be described by some point P in what we call as the space of theories. So the goal of the renormalization group formulation would be to try to implement the notion of a scale transformation, and the scale transformation is described by a number, a real number S, which is typically greater than 1. And what we do here is we try to coarse grain, that is we try to look at the system on longer scales, on larger scales, and basically we are trying to find out what are the infrared properties of the theory or properties of the theory at very low energies. And this produces this RS transformation, it produces a flow in the space of theories, and this is what we mean by this P of S, RS when acting on a point P. We will take it to some new point which depends on S, and that is why we call it P of S. So Wilson's very beautiful formulation takes 3 steps to construct RS. The first is you take the fields that you have and you break them up into long wavelength pieces, which is given by phi less than, and short wavelength pieces, and the short wavelength pieces are determined by the parameter S. So they contain all the wave vectors, all fluctuations with wave vectors which are between lambda by S and lambda, where lambda is the momentum cutoff. And phi less than has the modes that are of longer wavelength or shorter wave vectors than lambda by S. So once you do the splitting, the first step is to integrate out the short wavelength modes, namely the phi greater than modes, and this will generate for you an effective action for the phi less than modes. This effective action for phi less than modes is now defined with a cutoff which is lambda by S. So if you want to now think about comparing two theories, you cannot compare the original theory with this one because your cutoff has changed. So the idea to try to restore back the cutoff is to rescale, which is where you are doing the scale transformation. And when you rescale, you have new coordinates which are x by s and new momenta which are s times k. The positions and momenta transform in opposite ways if you wish under the scale transformation. And you also transform the fields. So you find these intermediate new fields phi tilde nu, which are related to the old fields. So this should be phi less than, sorry, there is a typo here. So this should be phi less than, and this uses the new action for phi less than in terms of these new quantities. So the effective action is now written in terms of these phi new quantities. And the final step is probably the most sort of new step in the sense that one may not have encountered this in elementary physics courses definitely. So the idea is to try and see whether we can restore back the Hamiltonian to what we started off with, at least for some set of coupling constants, in the sense that we are already being in the vicinity of some kind of fixed point. And the way this is done is you define the intermediate fields as a renormalization factor zeta of s times this new field. This will be our really the new fields, and we choose zeta of s in such a way that some one constant in P, one coupling constant in P does not change. So typically this would be the coefficient of the gradient phi square in the ON theory, because that's the that theory is what describes the fixed point, the Gaussian fixed point, right? So that is the idea of the renormalization parameter, and this renormalization factor arose in field theory in many different contexts, and this has now taken its own place, and It's called the renormalization group. So this procedure will induce this flow from P to P of S, and there is a very nice differential version of this flow one can write down. So what one writes down is, if you parameterize S as e to the power L, so what you're doing is you're sort of taking the logarithmic derivative with respect to S of this quantity, and then you will see that you will get something called the beta function on the right hand side. So in a sense you can say that the goal of renormalization group is to derive this beta function. And why are you interested in the beta function? Because if you solve the beta function equal to 0, that will give you the set of fixed points of the theory. And if you take this fixed point and study the neighborhood of the fixed point, as we have seen before, the linearized version of the renormalization group transformation about the fixed point can tell you about the critical properties about that fixed point. So what we achieved in the last lecture was that we used this formulation to solve the Gaussian model using renormalization group. Of course, we can solve the Gaussian model exactly, but we did not do that. What we had done that previously, but we recovered all the results of the Gaussian model from the renormalization group calculation without explicitly finding the free energy and stuff of the renormalization of the Gaussian model. Using renormalization group, we solved this. Okay, what will we do in this lecture? So remember, last time we derived some flow equations for the parameter t, which produced a correlation length for the Gaussian, about the Gaussian fixed point, and we saw that the flow equation was dt by dl is 2 times t, and we noted that this 2 was somewhat interesting, and in general one can ask what determines these exponents corresponding to the eigenoperators of the differential form of the renormalization group flow. So this is our this will be what we will be discussing today first, and then what we would like to do is after this discussion we will realize that we have to actually study the ON theory with not just the Gaussian quadratic terms, we have to also include some other terms, and you will see that when you start, you may think, oh, the problem is quite difficult because you may have to introduce lots of terms, but you will see that you don't have to, and I will show you that. In fact, understanding the meaning of the RG flow will already tell you what are the important terms to keep and so on. So this is what we are going to do today. So let's start by just quickly looking at the ON symmetric Landau-Ginzburg theory. So what we typically have done is we have kept up to quartic order, but today we will not do that. We will take this Gaussian theory, we will keep this term which is t, we will call this as S0 phi. So this is in a sense our base theory, in the sense or the theory that we, let's say, understand fully well. And what we are going to imagine is that we are going to imagine perturbing this theory or adding to this theory a bunch of terms. In fact, a lot of terms. We are going to add many all possible terms if you wish. So what kind of terms can we add? So I just introduce a little bit of notation here. So this is a very crude but hopefully helpful notation. So what this is telling is, it's telling that I'm going to write down a term with m nabla derivatives. This is nabla is the gradient operator. M nabla derivatives. That means there are, if I expand out this term, m nabla derivative terms will appear, and there are m phi powers of phi. Okay. So let me illustrate this. So if I take this term in the language that I am introducing here, this term will have m nabla equal to 2, because when I expand this out, I'll get two gradient terms will be there, gradient phi and another gradient phi, so that m nabla will be 2, and phi there are two powers because there is gradient phi and yet another gradient phi, so there are two powers of phi, and that will give me m phi equal to 2. So here I am not including 2 and 2 here, so you can assume that these two terms are not included here, but all other terms are included here. For example, I could have m delta is 10 if you wish, and I could have m phi is 26 or whatever. I need even numbers because I need symmetry, right? So this is what I have just introduced here. So this is a symmetry allowed term. So of course, when you introduce gradients, etc., you should make sure that they're spatial scalars, they're rotation scalars. You should take care of all of that. Let's say that you have done that, and we can give some examples which are not included here. So suppose I take m nabla is 2 and m phi is 4. Then I could write a term which is gradient phi square times phi square. So this is an ON scalar as well as a spatial scalar, rotation scalar. It's all kinds of, it's a nice operator. Okay. So you may think, okay, if I say m delta equal to 2 and m phi equal to 4, this is the only thing I can write down. So you'll see that my notation here is a bit scanty, but okay. The idea is that given m phi and m nabla and m phi, there can be many different types of terms, right? So for example, m nabla equal to 2 and m phi equal to 4, the example we discussed before, you can write down yet another operator which is different from the operator that we have here, and that operator goes like this. So it is gradient of phi square. So when you do phi square, you get a ON scalar. You take a spatial gradient of that and dot the spatial gradient with itself. That's what the square here means. So the square is actually dotting on the spatial gradient. So what you're getting is you're getting a spatial scalar, and the other quantity inside is already a ON scalar. So this is also yet another operator. So the idea is that we're going to sort of club all this together, and we'll just write a generic form like this. So if you know some particular operator, you can write it down explicitly and so on. But for our purposes, this will suffice. Okay. So our first point to note is that we have introduced the notation P here. P here means that this quantity Gp of m nabla m phi, that's the coupling constant associated with this operator. That operator has some physical dimension. How do we determine the physical dimension? We always determine this physical dimension by looking at S0. Now in S0, we have chosen the coefficient of gradient phi square to be 1 because we are sort of hanging around near the Gaussian fixed point. And at Gaussian fixed point, if all terms T and Gp are all of them are 0, then that's the fixed point. And so we under RG, we want this to come back to itself. So we have chosen this to be dimensionless and unity. Once you fix that, then it will fix the dimension of the operator of the field phi, and we know the phi has dimensions length to the power minus d minus 2 by 2. I hope you remember that. And then you will be very easily able to compute the dimension of this Gp, the physical quantity. So this goes as L to the power m nabla plus d minus 2 by 2 m phi minus d. So this is what will be the dimension of this operator, of this coupling constant, sorry. So now once I have this, I have a natural way to characterize this, this dimensionful coupling constant in terms of a dimensionless coupling constant. So I have dropped this P here and I am calling this G m nabla m phi. And what is a natural choice of dimensions that I have? It is, I need L. So I take lambda inverse. So I just get a minus sign on this and I will end up getting this power. Okay. And now these are the dimensionless coupling constants here. Okay. So now I choose to work with in the space of theories. I'll choose to work in the space where all coupling constants are dimensionless. So this P now is written as 1 T and this dimensional, the set of all these dimensionless coupling constants. So it's some very large dimensional space. Okay. So this is what we have. Now what we're going to do is we're going to do RG on this. And you will see the title of the slide says tree level. So I'll try to explain to you what that means. So I'll go through this slowly so that we sort of internalize this method of renormalization group. So what we do is we take this field phi of x and split it into the long wavelengths and the short wavelength fluctuations. So remember, the short wavelength fluctuations have all the momenta between lambda by s and lambda, because we are trying to construct a transformation with s as a parameter. Now what we are going to do is, we have this action which we have written down, this action, and here I need to stick in phi less than plus phi greater than. So I have done that, and then what I do, I go term by term and expand the terms in terms of phi less than and phi greater than. What I do is, I collect all terms that only have phi less than and club them together, and you will see that if you just a moment's thought will tell you that that is gotten simply by putting phi less than into this expression, and that is why we call this S of phi less than. And the extra terms that I will get either have both phi less than, phi greater than, or have only phi greater, right. So there can be terms with both of them, and there can be terms only with phi greater than. So you collect all of them together and call this u tilde. We will see why we are calling it tilde. There is this again is going to be something intermediate. We'll see that much later, but let's continue with this. So we'll call it u tilde phi less than, phi greater than. This is what we call this. This is just a formal splitting of the action. So now I have to integrate out the short wavelength modes to get the effective action of the long wavelengths, of the longer wavelengths. So this is my definition. S effective action of phi less than is equal to e to the minus s phi less than times, you have to do the integral, functional integral over all the modes that are the fast modes between lambda by s and lambda, namely phi greater than, and you have to integrate e to the minus of this quantity. So this is the idea. So what is the tree level approximation? So the tree level approximation for renormalization group is, at first sight you might think is just being lazy, but it's not quite so, because it will teach us a lot of things, is to simply say that I am going to take this and pretend that this is not a function of phi less than at all, and that this is some constant, right. That is like saying that this is taken to be 1, if you like. Why am I saying 1? If it is a constant that does not depend on phi less than, then you can write it as e to the power some other constant, and that is like shifting the action by some number. So we know that that will contribute only to some analytic piece to the free energy, etc. So we don't even bother to do it, we just drop it, and that is the idea of tree level approximation. So now you may wonder, why is it called tree level? Okay, so we'll understand that probably at the end of this lecture, but the idea is that when you do these kind of integrations of objects, what you're doing is you're going to draw certain graphs called Feynman graphs, and these are the graphs which look like trees in the sense that they don't have any loops, right. That's why it's called tree level. So it's not very important to call it to fully understand why that's the case, but okay, in case you are curious. Okay, so what I end up getting is, the tree level approximation is practically speaking just this. It's saying that effective action of phi less than is simply our old action with phi less than inserted into the as an argument. But the important thing to remember is that the theory is not same as the S original action, because the cutoff has changed to lambda by S. Okay, so that is the whole point. So we just stick in phi less than in the theory. So the form of the action looks exactly same as what we had before. Nothing has changed. The coefficients are all the same. The coupling constants are all the same, but the cutoff has changed. So I cannot compare this theory with the theory I started off with, because the cutoff has changed. So I have to do some rescaling, etc. And that is how I am also checking whether there is a rescaling symmetry. Okay. So the process of rescaling and renormalization is actually very straightforward here. So I invite you to do that yourself, and you will see that since we are at the Gaussian fixed point, we are sort of perturbing around the Gaussian fixed point. You will see that zeta of s now goes as s to the power minus d minus 2 by 2, which is exactly what we had before. and this gives us the new action. And just to keep notation simple, I'm no longer going to write this new business, because I think by now you will be able to realize when we have done the integration that we have got something new. You will be able to see from the structure of the equations itself that that we have got something new. So what has happened in the new action? The new action has the same form as the old action. It can't have any other form because it's what is allowed by symmetry. Everything allowed by symmetry is included, so it cannot change. But the important thing is that the coupling constants have changed. So the coupling constant 1 does not change, and that's by design. We chose the renormalization factor so that it does not change. T has gone to S square, that is very familiar to us. And now look at this very interesting result. This G M nabla M phi, the coupling dimensionless coupling constant associated with this operator, it has changed. It has picked up a dimension. It has picked up a factor S to the power D minus 2 M phi minus M nabla. Okay, and remember that this theory now has a cutoff, which is lambda. So we can compare this theory with the old theory. And we can write down the beta function, and in fact this is the renormalization group transformation. R is acting on P1t, this quantity will go to 1t S square, and this G's will go to this. Remember, very important to remember, this is not the exact renormalization group equations. These are the tree level renormalization group equations, and what you see is that dt by dl is 2 times TL, and dg by dl is just this quantity. Okay, so we have figured out what are the dimensions or what are the critical exponents corresponding to these operators dm phi and gradient to the power m nabla phi to the power m phi. So the tree level exponents are mu t equal to 2 and mu m nabla m phi is equal to this. So now you may wonder, what exactly are this 2 and all of this? So just a moment's thought will tell you that that is the physical dimension of the coupling constant in the momentum dimensions. So they are like the lambda dimension of the physical coupling constant. So the tree level exponents are simply what I call mass dimensions in field theory, or in our language, the lambda dimension of the field theory, right? So you may wonder, what is so big deal about renormalization group? It's just doing dimensional analysis. Okay, so that is of course not untrue, but it will tell you something far more interesting and useful when you analyze it. So at tree level, it does just dimensional analysis, but dimensional analysis tells us a lot, as you will see in the next slide. So now the tree level renormalization group at Gaussian fixed point, for the tree level renormalization group, the Gaussian fixed point is a fixed point in the sense that if I set the beta function equal to 0, if I set these guys equal to 0, the right hand side, then t becomes 0 and this g phi becomes 0. So that is indeed a fixed point. And the question is, what are these operators doing around these fixed points? Are they relevant or irrelevant? This is the question. So first point is, because the scaling dimension of t is 2, that is mu t is 2, exponent is 2, t is always relevant at the Gaussian fixed point, irrespective of spatial dimension or symmetry. Okay, so this is the first point. Second point is, if you look at the expression for mu m delta, you see that when m phi increases, let's say you are in dimensions greater than or equal to, let's say 3, then as m phi, that is the number of powers of phi, increases, this mu starts to go down. So if you keep making m phi very, very large, so let's say 5 to the 26 or something, then you can expect this to go to 0, because go negative, because you see this is this d is fixed at 3, and then this will keep growing and then it will go negative. So you can see that if you start writing all possible terms, the higher power terms are definitely going to be irrelevant. One more very interesting result, the more gradients you take, the more irrelevant it becomes, because you see to this exponent you are reducing the number of gradients that you have. So if m delta is larger, then this will be smaller, which means its growth exponent is smaller. Okay. So what is this going to tell you is that we will now be able to classify all possible relevant and irrelevant operators simply by looking at this mu m delta m phi. So if to explore this, since we know that the more gradients we add, the less relevant it becomes, we will just look at what happens to phi to the m phi operator, the coupling constant associated with that, and m phi must be necessarily even for us to get symmetry, to get the ON symmetry, right? Otherwise you cannot get ON symmetry. So what we are going to do is we are going to look at m phi even, and what I plotted here is color coding like this. I have plotted this mu m with the following color code. It is red if it is positive, it is blue, namely marginal, if it is 0, and green if it is irrelevant. Okay. So let's look at d equal to 3. Okay, let's look at d greater than or equal to 4. So when you see d greater than or equal to 4, there is only one operator that is relevant at the Gaussian fixed point. What is that operator? That operator has m phi equal to 2 and the coupling constant there is t. So this is the result that it's all red here, is showing you that t is always the relevant operator. That's the point that we made before. Are there any other relevant operators? From dimension 4 upwards, no other operator is relevant at the Gaussian fixed point. So now suddenly this analysis helps us understand why is it that the Ginzburg-Landau exponents became exact when d was greater than or equal to 4. They became like the Gaussian exponents. We saw that the Ginzburg-Landau saddle point exponents were same as the Gaussian exponents, and Ginzburg-Landau theory becomes exact, saddle point approximation becomes exact when we are in d greater than or equal to 4. So now you see why, because at the critical point, so to go to criticality you have to tune t, and there is only one relevant operator at the critical point, which is t. So if you tune it to 0, you are at the critical point, right? Okay. Second, if I look now at d equal to 3, you see there is one relevant operator, one more relevant operator I should say other than t, and that is the phi 4 term, right? This operator, the operator corresponding to d equal to 3 and m phi equal to 4. That operator has a scaling dimension which is positive. In fact, it's 4 minus d, and so when d is equal to 3, it is positive and therefore it is relevant. Okay. And now you see this also explains the origin of universality. So we said that near a critical point, all the there will be only few relevant operators. So you can see that if you are in d equal to 3 near the Gaussian critical point, there are only two relevant operators. There is this t and there is this other phi 4 operator. So it tells you that near critical points there will be only few relevant operators, and it sort of comes from this dimensional analysis story. All other operators are irrelevant. So what happens is at the UV level there could have been many interactions in the Hamiltonian, etc. But the longer wavelength modes will see some effective action, or the effective Hamiltonian for the longer wavelength modes will have these few parameters which govern the physics. And in the context of this ON symmetric Landau-Ginzburg theory, we see that they are t and the coefficient of phi 4, which determines the physics near the Gaussian fixed point of such theories. Okay. So we have already seen from this renormalization group analysis two extremely important results as to why we now understand why Landau-Ginzburg saddle point is very good in higher dimensions, and also we understand the origin of universality in the sense that there are only a few relevant operators near fixed points. Okay. Alright, so now you will see that, okay, while all this is great in D3 and above, we see that in D equal to 1 and 2 things are very bad, because you see if at a Gaussian fixed point there are many relevant operators. So what this is telling you is that if you want to study critical phenomena where there is universality etc. that's showing up in lower dimensions, starting with a Gaussian theory is not a good idea. That's what this is telling you. Okay. And this we have already kind of seen this, because we saw that when you go D less than or equal to 2, the fluctuations start to dominate a lot. So you have to do something much better than Gaussian theory. So for now we will set aside D less than or equal to 2, and we will try to stay near D equal to 4. We will explore what is happening in D 3, 4 etc. Okay. So in some sense this slide here is one of the most important things that we have discovered by exploring renormalization group. It is the idea of how variety of phenomena that we see at critical points is explained by this within this framework of renormalization group. Okay. So now we know exactly what we need to do to try and understand the critical point in say D equal to 3 for some ON symmetric Ginzburg-Landau theory. So we need to keep only one term, namely this term, right? And that is the G04, no gradients and 4 powers of phi, and this is the term that's the relevant term near a Gaussian fixed point. Okay. So what I can now do is I can show you how the renormalization group flow occurs in D equal to 3 and D equal to 5. In D equal to 3, you see both T and G are T and U. So now we have changed the notation. G is called U by 4. Remember, we introduced U when we discussed Ginzburg-Landau theory. So you're back to that Ginzburg-Landau theory with U as the coupling constant, T as the dimension, little u and little t as dimensionless coupling constant corresponding to phi to the 4 and phi to the square. So this t is relevant. So what does that say? So if you are little away from 0, then you will flow away, and same thing now t less than 0 is allowed because I have some u as well. So the theory is well defined. And so if I have a little bit of u, it will flow away. So the point is that in 3 dimensions, this Gaussian theory has 2 relevant symmetry preserving operators. There is no magnetic field here. Magnetic field will be relevant. That's not the point here. The point here is that there are 2 relevant symmetry preserving operators. There is phi square and phi to the 4, both of which are ON symmetric operators. So this is a fixed point. The Gaussian fixed point has 2 relevant operators. On the other hand, if you are in D equal to phi, you see that this u is irrelevant. What does that mean? That means that you can start with some u, but at the longest scales, as if you want to tune the system to criticality, you need to tune only t. You need to bring t to 0, because even if there were u, it will flow on longer scales, it will flow to 0. So it will become a theory, it will effectively become a purely Gaussian theory. So you need to tune only one parameter to get to this critical point. But we know, for example, from experiment that in Ising model, if I have a 3-dimensional Ising magnet like lithium holmium fluoride, I need to tune only the magnetic field to 0. I keep the magnetic field 0, that is, I have to keep no symmetry, I don't want to have any operator that does not have Ising symmetry. I turn off the magnetic field, and then if I tune temperature, only one parameter, I will reach the critical point, right? Therefore, the real 3-dimensional Ising model has only one relevant operator at the critical point. What is that telling you? That is telling you that this Gaussian fixed point is not describing our ON symmetric or O1 symmetric in the case of the Ising model in 3 dimensions, right? So this suggests that this P star G is not the critical point that we are seeing. It could be some other system may realize it, but certainly it's not the Ising magnet in 3 dimensions that is realizing this Gaussian fixed point. Okay, all right. Now the question is, how do we access the other critical point? So here is where we are going to use this idea that, okay, I am starting with this fixed point and I am flowing away from this fixed point. Now if I, if I pour water from somewhere, the water will flow down, and if there is a sink, it will go to that sink. If there is no sink, of course it will keep flowing down. The question is there some sink here? Is there some place where this flow will go and stop? So is there another fixed point in the vicinity of this Gaussian fixed point which has only one relevant direction? So what will happen there? This flow will go and stop. Maybe there is one relevant direction. If you go orthogonal to that, you will flow away. So you are looking for a fixed point with only one relevant direction, and of course one irrelevant direction since you have 2 parameters here. And the question is, does such a thing exist and can we access it? So this is the idea. And so what we need to do is, we cannot just stick to tree level, because at tree level it will just keep flowing. I mean, this tree level just keep flowing and will go off to infinity. So that's not going to help us. So we have to go beyond tree level, and we have to change these renormalization group to include what people in field theory call quantum fluctuations. Quantum fluctuations is the loop terms, so not just tree level, right? And this analysis will require us to go beyond the Gaussian theory, and we have to develop some tools and techniques for this. So if you have done a course in field theory before, then of course everything that I am going to say in the rest of the lecture will be familiar to you, but I am not going to assume that. So what I am going to do is, I am going to give you a very quick review of field theoretic techniques, so you can think of this as a crash course. I hope it's more of a course and less of the crash part, but in any case, let's try. So we will start with the simplest version of beyond Gaussian to start whetting our appetite to get into this kind of calculations. Okay. So we are familiar with Gaussian probability distributions. So let's say that instead of the Gaussian probability distribution of one variable, I had a probability distribution which looks like our Ginzburg-Landau action. So what do I have? I have t by 2 x square. X is some real variable which can take values from minus infinity to plus infinity. And the probability that it will take value of x is given by this. And z partition function is of course a normalization constant. So I just have to integrate this and just divide by that, and that will give me the partition function or the normalization constant. Okay, so this theory is defined by 2 parameters, t and u. Now the natural question to ask is, what is the mean value of x square? Okay, I did not put this question explicitly, but please stop the video and ask yourself the question: if I turn on u, will the magnitude of x square, expectation value of x square, be larger than when u was 0, or will it be smaller than when u was 0? Please think about that before we proceed. Okay, so I am going to show you how to think about these calculations. So the way we think about this calculation is the following. We will say that magnitude of x square is, of course, you just put this probability distribution e to the minus x to the x square times this, and then divided by the partition function. So what I am going to do is, I am going to expand the numerator. So the numerator is integral x square times e to the minus t square. I am going to keep e to the minus t square here, and e to the minus u by 4 x to the 4, I am going to expand in power series. So that will be m equal to 0 to infinity, minus 1 to the power m by m factorial, u by 4, that is just this u by 4, x to the power 4m, because I am taking the mth power of this, and this plus 2 is because I am finding expectation value of x square. So I need to multiply this by x square, which I am shifting it into that. And the denominator is just this partition function expanded out in power series in u. Okay, now what I do is, I do a beautiful trick. I say that if I know what is the partition function when u is 0. So that's what I call z0, and we know that's just square root of 2 pi by t. So I just divide this by that and numerator and divide by z0. Oh, but then you suddenly realize that this is like taking the expectation value on the pure Gaussian. So that is why we call this as 0, which means that it is the pure Gaussian with the u equal to 0. And now you see, I have the numerator as a power series in u and the denominator also as a power series in u. And I know exactly how to compute the moments of a Gaussian distribution. Now the remarkable thing about the moments of a Gaussian distribution is the following. If you know the second moment of the Gaussian distribution, namely if you know the x square of the Gaussian distribution, then you know all moments. So another way of saying this is that the Gaussian distribution has only a single cumulant, right? So all the other moments are will be determined by the single cumulants. So in fact, what we can find is, we can find that x square, the mean x square on the Gaussian is 1 by t, mean x to the 4 is 3 by t square, and so on. And you can stick it into this expression and you can expand out and keep terms to leading order in u, which is linear in u. And so you will see that x square reduces, right? X square reduces from 1 by t by an amount which is 3 times u by t square. And that's not surprising, right? Because if I go further away now, the probability that I will be further away is reduced because of this u term, and this is why the mean square fluctuation comes down. Okay, so this looks pretty manageable, right? So the trick what we did was we took the numerator and denominator and found the values of those in power series in this u by finding their average values on the Gaussian that which we know how to solve. Okay, so now you will say, okay, this is all good, but I need to do field theory. I need to be able to do this for my ON symmetric Ginzburg-Landau theory. How am I going to pull that out? So the next step to do is, we saw this for a single variable. So what if instead we had a probability distribution in a vector space, a real vector space with n components, right? So this will be a multivariable probability distribution. So P of psi. So I'm writing this as e to the minus. It's a Gaussian in that in the space, in the vector space, with this term which is u by 4 psi transpose psi whole square. So this looks exactly like our Ginzburg-Landau Hamilton. Okay, so Z of u is exactly this matrix, is this integral, and this G inverse is an n by n matrix, right? You can think of it symmetric if you like, right? And when u equal to 0, we can solve this exactly, and that is the partition function when u is 0, so that become a Gaussian, and you can show very easily that this is z0 is 2 pi to the power n, n is the dimension of this vector space, times determinant of G. And you can also show something very interesting. If you have not seen this before, I strongly encourage you to work this out. You can show that the expectation value of psi I1, I1 and I2 can be any of these numbers from 1 to n, is the matrix element. So what you have to do is you have to take G inverse, take its inverse, so you will get G, and it is the matrix element I2, I1. Okay. So this is also a well-known result. Please check out suitable references if you have not seen this before. Okay, now comes an interesting question. What happens if I have higher moments? So for example, I take even powers of psi. So I take I1 component, I2 component, I3 component, I4 component, and I want to find what is the expectation value of this. Okay. So I am not going to prove this statement in this lecture. I will just assert what is known about this. So the way you do this is the following. You find all possible contractions. So what is a contraction? A contraction is a kind of pairing. So what you do? You take this pairing and that pairing. So if I now think of this pairing, you should replace it by this expectation value of this psi I1 and I2, and that we know is I2 I1, and then this pairing will be I4 I3. Now what you have to do is you have to do all possible pairings. So what are the all possible pairings? So I1 can be paired with 3 of them, I2 can be paired with the remaining 2 of them. I2 cannot be paired anymore, because once you paired I1 with one of the 3, then the other pairing is automatically made for you. So for this product of 4 psis, there are 3 possible pairings which I have listed. So I1 can be paired with I2, then this is automatically paired. I1 is paired with I3 and these 2 are automatically paired. I1 is paired with I4 and these are automatically paired. And you just do, whenever you see this, you have to replace it by this G term, which is the expectation value on the Gaussian. And that will be the expectation value of this object in the Gaussian ensemble. Ensemble meaning in the Gaussian probability distribution. So this statement is called as Wick's theorem, or a version of this is in some sense a very simple version of Wick's theorem. And this is the central workhorse, or the most important technical tool that we use to do field theory calculations. It's Wick's theorem. It's to say that if I have a Gaussian, then any moment of the Gaussian, however multidimensional it is, can be obtained as some set of all possible contractions, and each contraction will be a product of moments of this kind, right? So that is the idea. Okay, so with this background, we suddenly realize that we can actually evaluate Z0 by ZU by Z0. So what am I doing? I am taking the ratio of the partition function associated with ZU by Z0. So if I do that, so this becomes 1 by Z0, and now I can interpret this as the expectation value on the 0 ensemble, that is the Gaussian, of this quantity e to the minus psi square. This term I can now expand in power series, and now I will see that I will get this object as expectation value of psi transpose psi. So that's a number to the power 2m. So if you expand that out, if you expand that number out, there will be 4m powers of psi. So for example, if I look at this case, if m were equal to 1, then I will get a term correspond something like this. I will get terms of this kind. So now I can use Wick's theorem, do all possible contractions, and I will be able to evaluate this. As you can guess, this is going to be a bit of technical work, but if you think that it's going to lead to some interesting results, well, might as well do it. Okay, so that is the idea. Okay, so this is how we can find out a non-Gaussian or something like a Ginzburg-Landau some quartic term in the exponent of the probability distribution. We can handle this in this way. Okay, so strategically it's like you take the expectation value about the Gaussian and imagine that this U term is like a perturbation on the Gaussian, and you sort of expand out the probability distribution weight about the Gaussian, and you see the effects of the U term. So this is the idea, and you use Wick's theorem to calculate the higher moments of the Gaussian. Okay, very good. So we have now at least formally got an expression for the partition function of such a complicated model. Now let's see what we will do with our ON symmetric Landau-Ginzburg theory. Okay, so we just repeat the action here, and what I'm going to do, I'm going to keep this as S0 phi. So this has no U in it, that's why it's called 0, and it's the Gaussian piece, and the Gaussian fixed point will be described by t equal to 0. So this action is still Gaussian in the sense that it is quadratic in phi, and you have this term, and I cannot overemphasize this point. Always remember that there is a cutoff in the theory, and that's lambda. So our goal is to obtain the partition function as a functional integral on this when u is not 0. And as usual, what we will do, is we will try to understand the theory with u equal to 0. And what I am going to do is I am going to take this theory when u equal to 0 and I am going to try and massage it to a form which looks like our multi-dimensional example that we worked out, or the multi-dimensional instance of this problem that we worked out in the last slide. So if I take z0 is this, then I can write this as, just put u equal to 0 and then s0 will become just s0, s of phi will become s0 phi. And the important thing I want to emphasize to you is that this problem, this action can be cast in a different way. How would you do that? You see, there is a single integral in position here. What I am going to do here is I am going to make this into an integral in 2 position coordinates. How do I do that? I introduce some quantity. So now I have also expanded out this vector here. I am writing explicitly in terms of components, and repeated indices are summed. The Einstein summation convention is assumed. Alpha 1 is summed, alpha 2 alpha is summed over all possible little indices. So this is what we have here, and G inverse of x1 x2. So what is this quantity G inverse of x1 x2? So what I do is I take this term, and you see it said that's gradient phi dot gradient phi. Now what I do is I do integration by parts, shift one of the gradients to the other term, so that becomes del square now, and so I'll get phi minus del square phi. And now what I do, I introduce the other term here. You see, this one does not have any, this operator will not have any alpha dependence. So I put a delta function in alpha and alpha 2, so that only the individual components talk to each other. And I introduce this delta function because this thing has only one coordinate, and this is what I call g of x1 x2, and the action can be written out in this form. Now you realize that this looks exactly like a matrix problem. So imagine that this is like it's a vector with continuous indices. So this alpha 1 x1, if you club that into some kind of index, and this one has some kind of index, so this psi transpose G inverse psi, which was like some matrix multiplication, this can be thought of as a matrix multiplication with continuous indices. So what I am trying to impress upon you is that this has exactly the same form as the multidimensional problem that we studied, except that the multidimensionality is in some sense a continuous index, right? Okay, so that's the idea. And if we now want to compute what this quantity is, we have done this exactly when we are doing fluctuations in the Ginzburg-Landau theory. So if you do this, you will see that will turn out to be this inverse of this G matrix, the inverse of the Helmholtz operator, if you like, and you will see that it is this term that we have, and we have computed this before, and that's why this recall is here. Okay, so if you're coming from the field theory perspective, this quantity is sometimes called the Green's function or the propagator. It's just a term, okay, and we can also use that language if you feel necessary. So the idea is that this G alpha 1 alpha 2 of x1 x2 has this delta alpha 1 alpha 2 index, so it's diagonal in this ON space. So it's ON symmetric if you wish. It's like a scalar in the ON space if you like, and this is what we call as G of x1 x2. This has no labels, this quantity. So this is that term which looks like a power law at distances smaller than the correlation length and looks like exponentially dying when distances are greater than the correlation length, which is given by this T lambda square. The whole inverse square of that is T lambda square is 1 by C square is what I am trying to say. Okay, so that is the propagator. Okay, now we are ready to do some more complicated calculations. So what if I have 4 such terms? I have 4 fields and I want the expectation value in the Gaussian ensemble. So what's the rule? just Wick's theorem. So what you do this contraction, this contraction, this contraction, this contraction, this contraction, this contractions. There are 3 of them because there are 4 fields. And what you do, whenever you see this contraction, you replace it by this G, and when you see this contraction, you replace it by that G. For the next contraction, for the next set of different combination of contractions, you do the contractions and replace them by the appropriate values. And therefore, this expectation value can be explicitly calculated. Everything about this is known because we know this function. So the idea is that we can calculate any correlator of the Gaussian theory using Wick theorem by doing all the contractions and all the different contractions and adding them. Okay, so that is the message. So with this understood, we can now write down the partition function of the system with interaction or this SU, the phi 4 term U, in the following way. So the numerator is of course e to the minus S naught, e to the minus SU divided by the partition function of the Gaussian theory, namely the one with U equal to 0. But this by definition is expectation value on the Gaussian theory of e to the minus SU, which we now expand in a power series, okay, and I have just written minus 1 to the power m factorial. I take the power of this and raise it to the power m. Remember, this is a number for any given field configuration, and this to the power m, and I take the expectation value on 0. And the main idea is that if I have this, I can use Wick's theorem, this idea, to evaluate terms associated with this thing. Okay, so that's how we do this. So let's push on and let's see what happens when we try to compute something in first order in U. Okay, so SU is this. So first order in U, I am claiming is equal to this quantity. So now you see, I just wrote this as if there is magic here. So you see, now this starts to depend on the ON, it starts to depend on N. How did that happen? And how did I get this down? Okay. To see how I got this, you can directly go and apply Wick's theorem. You can write all these terms out. You see, there are 2 repeated indices here, 2 repeated indices here, they are summed. So you see, this will produce 3 possible contractions, right? So you can contract this with this and that with that. That will give you xx, so that you will get gx square, and you see that will produce n terms associated with this alpha. That's why this n comes here. Another n terms associated with this. That's why you get n square, right? Because I have to sum over all alpha and sum over all gamma. Then there is another contraction. I can contract alpha with gamma, this contraction and that contraction. So that there are 2 ways to do that, etc. So I am going to show you explicitly. So this whole calculation can be organized by what are called Feynman diagrams. So how do you organize this in Feynman diagrams? So whenever you see a term like this, you say that this point, this dark spot here, you think of it like this thing, and the point in space, if you like, where you put this point, you can think of as this position x. And of course, you will integrate over all x later. Now what you are doing, you are going to do contraction. So the first way of contracting is you contract this with this, please follow the cursor here, this with this, and this gamma with gamma. So what I will do, alpha with alpha and gamma with gamma. So you see, I am going to contract alpha with alpha and gamma with gamma. So contraction is achieved by simply connecting the open leg with the other open leg. So that's what is done here. So you contract like that, right? And similarly you do this, that is the gamma contract. Now this, the way I did this contraction will produce n square terms. Now there is another way of contracting. You can do alpha with this gamma and that with that gamma. So alpha will be forced to be gamma, but then both of them will go over n, and so you will get only n terms like this. Now there is yet another contraction. I can contract alpha with this gamma and alpha with this gamma, and that will give you this term, that was also n. And what is this line telling you? So you started off with x and ended back at x. So that's why it's called gxx, right? So if the line starts at some position, so this should be thought of as some position, and ends up at some other position, whatever is the position is there, it will just pick up x1, x2. In this case, x1 and x2 are the same thing, and therefore it is the g. So the way you interpret this diagram is, this quantity is this u lambda to the whatever, and these is one Green's function, another Green's function, they are starting and ending at the same place, and there are two of them, there is two lines here, so that's why xx whole square. And these factors are symmetry factors, coming from what symmetry you have in the system, okay? And they can be symmetry factors, and of course there are sometimes also called degeneracy factors of these diagrams. So for example, these diagrams are actually the same, right, in terms of alpha, gamma, they are actually literally the same diagrams, but they come with that factor, and then there is the symmetry factor n. So 2 times n is where you get this. So you see, this is a very, very efficient way of doing the calculation, thinking in terms of this diagram, and this idea was brought to physics by Feynman when he started thinking about quantum electrodynamics, I believe, in the late 40s and early 50s, etc. Okay, so the picture, as I explained, is that this dot should be thought of as this quantity and the line should be thought of as g. So you can, just by looking at this picture, you can find the value of such a diagram, right? Okay, so this is very good. So we have actually computed the first correction to the partition function, because if I get this expectation value of S0, I've got my first correction to the partition function to order u. So of course you don't want to stop here, you want to see whether you can push forward, right? So let's try to go second order in u. So if I write this out, then you see this is a functional. So there will be two spatial integrals, dx1, dx2. There will be square of this quantity. So there will be two powers, two terms, one corresponding to x1 and the other corresponding to x2. So in total there are 8 phi operators here, right? There are 8 phi fields here. So if you work out how many ways you can contract it, you will see that there are 105 ways. This is at the second order. So you're already wondering whether this is really worth it, and you start, you hope that if you start doing this kind of work, that something nice comes out of it. But I'll show you that yes, I mean there are many contractions, etc., but you can think about them and figure out some very clever ways to find out all of them. So you will see that among these 105, you can find out how to calculate. There are only few quantities you need to calculate, and the whole thing can be organized in this fashion. So you see this term phi alpha 1, gamma 1 at x1, that is what is this term here, and all other terms are at x2, right? So this is x1, x2, and you see I can do now contractions. So what if I choose this, there are 7 possible ways I can contract this with the others, right? And now you can, if you do the combinatorics, you can work out 105. So you see there are different ways of contracting this now. So the first way of contracting is, you contract this alpha 1 with alpha 1, gamma with gamma 1, this with this, this with this. So what we are doing is, you see there are these two, there is SU of phi and there is another SU of phi. When you are contracting amongst themselves. So this will lead to what are called as disconnected diagrams. So if you look at the diagrams that you get by contracting this with itself and this with itself, you will find that they look like product of diagrams of order 1, hence called disconnected diagrams. And you will see that the factors associated with this is n square times plus 2n, exactly what we had before, and the other is that, and so the factor going around with this will be just this quantity. And you see there are these 2 black dots, so I have to take this quantity and square it because there are these 2 black dots. And now look at the Green's functions. Both these Green's functions start at x1 and end at x1, start at x1 and end at x1. That's what this x1, x1, x2, x2. That's why there are squares of these. Okay, straightforward. All right. Now I start showing you disconnected diagram. So here is an example I can get. So I can contract alpha 1 with alpha 1. Then I can contract gamma 1 with this gamma 2. Now I can contract this. So I'll kind of get this kind of diagram. Now you have to work out how I pulled out this factor here, 8n cube plus 3n square plus 32n. You can figure it out. It's a very interesting exercise. And now you will see this will have three types of Green's functions. There is the x2 that is this thing. There is x1 that is that thing. And there is x2 there are two of them, therefore square of that. Okay, and in this case all four lines from here are contracted with all the four different lines on this side, and this will come as gx2 whole to the power 4, and you will get a factor which goes as 8n square plus 16n. Okay, so now I'll show you that this is all I think it's okay, and the idea is that if I take 1 plus 2, 3 square, that is 9 plus this is 64 plus 8 is 72, 9 plus 72 plus 24 should be 105. I think it's correct. I hope it's correct, otherwise it will be slightly embarrassing. Okay, all right. So that is the story. So you see you see that yes, this looks a bit daunting, but there are systematic ways to do this calculation. Okay, so we have done at the second order. So no, I am not going to do the third order, right? But what I am going to do is I am going to, based on this calculations we have done, what have we learned? That is what I would like to explore. So if you collect all the terms at the second order, you will see that this is the disconnected piece, and that comes as integral over position, right? So if integral over space, this can be thought of as some kind of density of some kind, right? Because integral over space is coming, and this is square. So in some sense, if this were a finite system, this quantity would be proportional to the square of the volume of the system. So this we would think is not correctly extensive. The first connected diagram, the one with that look like with two ears popping out and so on, that one looks like this. So these are all some numbers. So there is an integral over r of g of r whole square. This certainly will not diverge in the large distances, because I have a t in the problem which will kill this g of r exponentially at large distances. And to get here, to get to this form, I played a small trick here. Let me explain to you how I did that. So you see, so this is dx1 dx2 of gx2 x2 x1 x1. Since the problem has translational symmetry, we are not breaking translational symmetry, gx2 x2 and x1 x1 will not depend on the value of x2 or x1. On the other hand, this gx2 x1 will depend only on x2 minus x1. So I can choose 0 and x2 minus x1, and I can reparameterize integral over x1 using the center of mass coordinates x1 plus x2 by 2 and x2 minus x1 as the other parameter. So it's a little bit of work, but okay, you can do this. It's very straightforward. The Jacobian of the transformation is 1, and therefore I can, that dx1 dx2 can be converted to the center of mass coordinates and the relative coordinate of these things. And remember, gxx does not depend on what is the value of x, so you can think of it as g0 comma 0, that's also fine. And this is the integral over the relative coordinate now, integrated over this thing. So this and all of these are just numbers. So this, interestingly, is correctly extensive because this is a number, it's some kind of density, and if I integrate this, I am getting some number, and it will be proportional to the volume. Of course, we are working in the infinite continuum, so it's formally infinity, but it has a correct meaning of density as you are seeing here. And here I have this integral over this density as well. So I get these two, and these are all reasonably okay. So what is the thing that we have learned? We have learned that at every order, so we did only two orders, you will get connected diagrams and disconnected diagrams. Connected diagrams are correctly extensive, right? They will be always proportional to the volume if you wish, right? Disconnected diagrams are not correctly extensive. There will be some higher powers of volumes, okay? The most interesting result is that the disconnected diagram of order 2 is exactly the square of the connected diagram of order 1. And this is not magic, it's there, it happens for a reason. Okay? And to understand what is the significance of all this, we need to go and look at the free energy. So now we expanded the ZU, and we now in principle we computed this up to order 2, but we can in principle compute it up to any order, and therefore what we will do is say that we go to the mth order and compute this quantity. Let us just call it formally something called UM. And so UM will be proportional to little u, our dimensionless coupling constant of the 5-4 term, to the power m. That is just straightforward, right? So what I am going to do is, I am now going to compute the free energy difference of the system with u and system with our Gaussian thing. So what do? I take minus log of this, so that will be free energy with u minus free energy at 0. And what I do, I have this expansion here, so I take log of 1 plus this whole thing, so there is a little bracket missing here, right? Okay. And now I think of this as small quantity and expand. So it is u1 plus u2 minus 1/2 u1 square, and it just keeps going. So log of 1 plus x is x minus x by 2 plus x cube by 3 and so on. That is what we are using. Okay. So now you see this is u1 plus u2 minus half u1 square. I reorganize this and see. So now do you see something very interesting? You see immediately that the disconnected diagrams will get cancelled correctly. So u2 will have half factor times the square of the diagram of u1, and so that will exactly cancel out, and you will see that the free energy will be correctly extensive. And this is not an accident, as you know by now. We have also seen something very similar happening in the Ising model. Okay, so based on this, we can now find out what is the difference of the free energy density. So free energy density is simply what is sitting inside this integral. So I just collect all those terms, and that free energy density you can write it out like this. Okay. Now within our theory, unless there is some kind of divergence coming from long wavelengths, everything here will be finite because our ultraviolet is cut off by lambda. So things may be very strongly dependent on lambda, etc., but you will have this nice result here. Okay, I just want to make one small technical comment. It may not be very important for us at this stage, but later on when you want to do research and if you want to do RG and do some critical exponents, etc., correctly, then you have to know this. You have to remember that this is not some kind of Taylor expansion. In U, it is what is called as an asymptotic series. This is because if u is less than 0, our function integral is not well defined, because then the energy can be arbitrarily negative, right? And so then that's a problem, and the theory is not well defined. So one doesn't expect this to be like some convergent series where the higher terms are smaller than the previous terms and all of that stuff. So yeah, so this is what is called as an asymptotic series. So you please refer to suitable literature to figure out more details about this. Okay, so we have seen quite a bit today, so it's a good time to summarize. So we started off by discussing Owen-Ginsburg-Landau theory and viewed it as a perturbation of the Gaussian theory. We learned from the tree level renormalization group that the exponents associated with the operators turn out to be at the tree level the dimension measured in lambda, that is the cutoff. So if an operator has lambda to the power 3 as its dimension, then the renormalization group of that coupling constant of that operator, if the coupling constant of an operator has dimension lambda to the power 3, then the flow of that operator will be dg by dl will be 3 times g, right? So something like this. And in d equal to 3, we found that there are only 2 operators that are relevant, namely t and u, and the fact that there are no other relevant operators near this fixed point, already tells you that something like universality is sort of is there, because the system, all the other parameters that enter the theory is simply forgotten when you come to these critical points. And it also explains, since there are no other relevant operators other than t in dimensions 4 and above, you also see why the saddle point Gaussian approximation works so nicely there. So we also now understand that the Gaussian fixed point in d equal to 3 is not the candidate fixed point for the ON symmetric critical point, because of the observed point that there are two relevant operators there, but we know that the ON symmetric critical point should have only one relevant operator. We certainly know that for O1, which is the Ising model based on laboratory experiments. So this requires the strategy. What we are going to adopt is, there is a relevant flow, so you are flowing away from this Gaussian fixed point. The question is, will you flow to some other fixed point which has only one relevant direction? If we can pull that off, then that could be our, that we can reasonably believe is going to be describing the critical point, that is the what is realized in, say, in three-dimensional Ising model. And so for doing these calculations of figuring out what is the fate of this thing beyond the tree level, we explored methods of doing calculations, and this is what we call as the the perturbation theory. And we looked at diagrammatic method, and we looked at connected and disconnected diagrams, etc. Okay. So what's coming in the next lecture? Well, in the next lecture, what we're going to do is we're going to take these results and we're going to hunt for that new fixed point. And in fact, it will be the culmination of all the work we have put in, including listing out 105 contractions, etc. And so I'm sure you will want to join me for that. So I'll see you in the next lecture. So thank you very much.